This is the class notes for section 9.1. This section is called Naming Ions, and we're going to work through some of the information that's background after you've read about naming ions. So first off, we'll look at the ideas behind monatomic ions. And just as a reminder, monatomic ions are those single atoms that either have a positive or a negative charge. And for your class notes, if you're determining that positive charge of a cation, it is equal to the number of electrons lost from the atom. So the number of electrons lost from an atom, so if you lose 2 electrons, then the positive charge that you're going to have is 2 plus. So I'll do an example here, i.e. lose 2 electrons means a 2 plus charge. All right, now if we're looking at cations again, cations from monatomic ions are formed from metals. Okay, so a metal that loses 2 electrons is going to have a 2 plus charge. A metal that loses 1 electron is going to have a 1 plus charge. When we name those cations, again, we just keep the name of the metal and put the word ion after it. For example, if we have Na with a 1 plus, that is the sodium ion, and Ca with a 2 plus is a calcium ion. For anions, these are formed from nonmetal, and the value of the negative charge of the anion is equal to the number of electrons gained by the atom in order to get to octet. So this is the number of electrons gained by the nonmetal atom. And again, an example would be that if something gains 1 electron, that means that that ion will have a 1 minus charge. If it gains 2 electrons, it will have a 2 minus charge. So examples there might include chlorine, Cl1 minus, which is called chloride. Remember that the names of anions are going to have the ending dropped from the nonmetal name, and they will have an IDE ending. Then we get to the idea of transition metals. So the charges of the cations of most transition metal ions have to be determined from the number of electrons lost. And we have a couple of different naming systems that we use. So the naming of metal ions that can form more than 1 ion can be named using what we call the stock system, and that is our preferred system. In this case, we place a Roman numeral in parentheses after the name of the element to show its charge. That element is going to be a transition metal. Okay. So an example is if we have iron with a 2 plus charge, then because iron can have a 3 plus charge as well, we need to show that specifically we have iron 2, so Roman numeral 2, and let's say that's iron 2 chloride. So that would be with Cl1 minus. There's another system that we don't use very much that is called the classical system. In the classical system, this uses a root name like ferric for iron. So it uses a root name of the element with the ending with different endings. And the ending can be either OUS or IC. So if it is an ending of OUS, that means a lower charge. Or an ending of IC for a higher charge. A disadvantage here is it does not tell you the charges. So the classical system is considered pretty outdated. We don't use things like ferrous and ferric. We will use the Roman numeral in parentheses after the name of the charge. Some of the examples that we have using the stock system and the classical system, I'm going to show at the top of the next page. So for example, this Fe2+, the name of this ion would be iron and then Roman numeral 2. Okay, so that would be the name for that cation. Alternately, Fe3+ would be iron Roman numeral 3. In the classical system, the iron 2 would be called ferrous. So the root is fer for iron. And for the Fe3+, that would be called ferric. For tin, which can have also multiple possible charges, and that's why we have these different systems. In the transition metals, the multiple charges make it confusing. It's different from, say, just potassium, which can only form a +1 ion, or just calcium, which can only form a +2. The metals that we have in group 1 and group 2 are very predictable in terms of their ionic charge. These transition metals can have multiple possible charges, so we have to have a means of determining what the charge is. So for tin 2+, if we were to have that in a name, we would show that as tin 2. And for tin 4+, the IV is the Roman numeral for 4, where the V is a 5, and then the one that precedes it makes it a 4. So it subtracts 1 from it. In our classical system, this would be stannous. So the root for tin is stan, S-T-A-N-N. So it would be stannous for the +2 and stannic for the +4. Again, this is the method, using Roman numerals in the name is the method that we will use in this class. The classical system is not that important for us. You do not need to memorize these, okay? But you do need to know how to use the Roman numeral system. Every once in a while, we have some transition metals, however, that can only have one possible charge. So just as a reminder with our periodic table, that group 1, these cations that form can only have a +1 charge. Group 2 cations can only have a +2 charge. The transition metals are those metals that are found in the D block. But this multiple possible charges also applies to metals that are below the stair-step line in the P block. So we always have to check to see where a particular metal is to determine, does it have a predictable cation charge like group 1 or 2, or does it have possible variable charge, and is it in the transition metal and below the P block group of metals that can form potentially multiple cations. Now, within our D block and P block metals, there are 3 elements that are metals that form only one possible charge when they ionize, and that is silver and zinc and aluminum. They're in this diagonal right here, and for silver, that can only have a +1 charge. Zinc can only have a +2 charge, and aluminum here in group 13 can only have a +3 charge. So we're going to put those into our notes, which are transition metals with only one ionic charge. That would be silver, which can only form Ag1+. Okay, so that's our +1. Then there is zinc, which can form a +2 charge. And the element that's right below zinc on the periodic table here, cadmium, it also can only form a +2 charge. So I'm going to add that one in, cadmium. And that is Cd2+. And then, of course, we also have aluminum. So aluminum can only form a 3+. On your periodic table, feel free to write in those cation charges as you start to learn about these. So these 4 metal cations that are in the D block or P block below the stair-step line, these are the only one of those types of metal cations that do not need Roman numerals to show charges. So make a note to yourself, these metal cations do not need and will not use Roman numerals to show charge. Next in the 9.1 notes, we're going to look at polyatomic ions. And as we start to talk about these, you should realize that polyatomic ions, unlike our monatomic ions, monatomic meaning only made up of one atom, polyatomic ions are composed of more than one atom that are covalently bonded together into a group of atoms that have either lost or gained electrons. So this group of atoms has a charge. The name ending for most polyatomic ions is going to be either ate or ite, like sulfate and sulfite. Important exceptions to this include cyanide, which is Cn with a 1- charge, and that cyanide is a polyatomic ion. Unlike most of the monatomic ions, that's a polyatomic ion with an ide ending. Another one is hydroxide, OH with a 1- charge, that has an ide ending. And then ammonium is a little bit unusual. That is a polyatomic ion with a 1+ charge. The difference between those different polyatomic ions with ate and ite is if you see the ending ate or ite, these endings tell you that you have oxygen as part of the polyatomic ion. So ate or ite are endings for the name for polyatomic ions that contain oxygens. So not only do they contain oxygens, but the difference between those is that the 8 for a particular set, like sulfate versus the sulfite, the 8 is going to have one more oxygen than the ite. So the 8 will have one more oxygen than the ite. Something else to know is that the 8 and ite for a particular set of polyatomic ions will have the same charge. But has the same charge. The endings do not tell you how many oxygens there are for a particular polyatomic ion. That you have to memorize. Okay, but you do know that if we have an 8, the ite will have one less. All right, for your polyatomic ion chart that you can see right here, I'm going to show you the completed chart, and where it says also called, you're going to need to add those names in. Okay, so I want to point out a few things on this chart. You're going to need to make polyatomic ion cards, flashcards, and then you're going to need to memorize these. Make sure that you write your chemical formula and charge correctly and the name. So here's something to realize. The NH41+, the ammonium polyatomic ion, is the only polyatomic cation that we use, and it's a very it's pretty atypical or not typical to have a polyatomic cation. So NH4 with the 1+ charge, that's ammonium. The ClO3 with the 1-, that's chlorate. NO3 1- is nitrate. So that 8 ending there, if we were to check and say, okay, we also have nitrite, we would know that that would be 1 fewer oxygen. So it would be NO2 for nitrite, but it still has the 1- charge. A very important polyatomic ion that is going to be found in compounds that are called bases is hydroxide. That's OH with a 1-. We've got CN, so a carbon and a nitrogen with an overall 1- charge here for cyanide. And then we get into our also calls. So this is important. In your book, we have CH3COO 1- and also C2H3O2 1-. This is just the same compound, the same polyatomic ion with the carbons written together with a 2 subscript as opposed to written separately, and the 2 oxygens written together with a 2. In the book, they call that ethanoate, and that is a name for this particular polyatomic ion. The preferred name is actually acetate. This is used much more commonly, and that's one that we will frequently use in our Chem 1 class. We also have a polyatomic ion that has carbonate here, but with a hydrogen as a part of it. In the book, they call that hydrogen carbonate. We use the term bicarbonate. Now, the bi does not refer to 2. The bi refers to a hydrogen that is a part of this, or in addition to the carbonate in this polyatomic ion, and it has a 1- charge. Same thing here for hydrogen sulfate. That's the term they use in the book. We prefer the term bisulfate, and the bi refers to a hydrogen along with the sulfate. You also have your carbonate And this is just CO3 with the 2 minus charge, that's carbonate. SO4 with the 2 minus is sulfate. If we look at sulfite, which we would expect to have 1 fewer oxygen than sulfate, which it does, SO3, but it has the same charge. Okay, so make sure that you can distinguish between those two. Chromate, that's CrO4 with the 2 minus, and then phosphate, PO3 with the 3 minus. So if we were to predict, what do we think phosphite would be? That would be PO3, 1 fewer oxygen, but with the same charge. So make sure that you have those polyatomic ions written out correctly. You'll be using these to put together flashcards for your polyatomic ions. So for a flashcard, you would write NH41 plus on one side, so make sure that you have the charge and the formula correct on that. And then on the second side, ammonium, so that you can quiz yourself on working with those different polyatomic ion cards. All right, that is the 9.1 class notes.